one of the reasons we're calculating the standard deviation, why standard deviation was so important, is because there's an interesting relationship between the way things distribute by chance, normally by chance, and this thing called the standard deviation. Okay, so I'm going to give you an example. For instance, let's say that let's assume for a moment that the weights of male students is normally distributed. Okay, so what are the properties of something that's normally distributed? Well, let's see, the curve, the distribution, or the histogram. Let's look at it as a histogram. If we draw a histogram representing all male weights, for instance, this box over here represents people that are males that are 100 to 110 pounds, and this is 110 to 120, and this is 120 to 130, and so on and so forth, 40, 50, 150, 160, 170, and so on and so forth, 180, and so on and so forth. When we say it's normally distributed, well, one of the things that we're saying there is that this histogram, the distribution that this histogram has, is kind of a bell-shaped curve, right? It's going to be very tall in the middle. In other words, the most frequent outcome is going to be people that are an average weight for the entire population. Then as we get further and further away from an average weight for the population, we get fewer and fewer people that would be in the bins that would represent the number of people of the frequency that are that weight, right? So if we look at it from the perspective of, say, a small sample where this is 20 people and this is 18 and this is 16 and 10 and 5, let's say, kind of a step ladder. It's kind of bell-shaped, but it's kind of a step ladder. If we keep increasing the number of people that we sample and we make the bins narrower and narrower, right, we're going to get closer and closer to, instead of a bunch of bins, a bunch of steps like this, closer and closer to a continuous line, which has the properties of being symmetrical around the mean. In other words, this side looks exactly like this, the mirror image of this size. And that has certain distribution properties as well. Okay. Well, first of all, because if this population is normally distributed, and whether or not we would sample anybody from this population individually, whether we would randomly pick somebody to sample from this population randomly, it's just chance whether we would sample a person that is on this side of the mean or on this side of the mean. In fact, the chance is 50-50 that I would sample someone that's less than the mean or someone that's more than the mean, right? Not much chance I'm going to get somebody that's exactly the mean. That would have to be kind of a rare event, right? Because, you know, with weights, we're talking about maybe, you know, something that could go down to ounces or something like that. So we'd have to be really lucky to get somebody that's exactly the mean. But we could say that chances are 50-50, since this is symmetrical, that we could be on either side of the mean. So we have a relationship between this area that's in this distribution and the probability of picking someone out that would represent that particular weight. The weight, the probability that we would pick someone that's towards the upper part of this distribution, right, is going to be pretty low, because it's a pretty rare individual to be that high up in this part of the distribution, to be above, say, 250 pounds, or to be below, say, 100 pounds for males, right? They're there, right? There's some people there, but the probability that we would select someone randomly that would be in that portion of the distribution is unlikely. And actually, the area of this distribution, just like the area of these bars represents a probability distribution, the area of this curve also represents the probability that we would select someone from this population that's in that part of the distribution. You could also, if you wanted to, look at it as just the population itself. The percentage of people in this population that are from that weight down, right? So it would be really nice if we had a very simple tool that would help us relate to how this normal distribution is laid out, how the areas in this distribution represents the probability of selecting an individual from that area, or the percentage of people from that population or subjects from that population or results from a study or something like that that might fall into that area. And fortunately, we do have a relationship like that. Okay, it's going to be our empirical formula. There's a document on Blackboard called Lab Session Normal Distribution Empirical Rule. I'm going to blow it up a little bit so you can see it a little bit better. And this is the relationship that, or an approximation of the relationship between the standard deviation and the distribution of probabilities in the normal distribution. Okay, so what does this tell us? Well, this tells us that between one standard deviation below the mean and one standard deviation above the mean, we have 68% of the population, or probability of having 68% of the results, right? Well, how about two standard deviations below the mean and above the mean? Well, if we add all this together, it comes out to 95%. And how about 99%? Well, how about three standard deviations? Three standard deviations, we have virtually all of the outcomes. We have 99.7% of the possible outcomes. Okay, so let me take this and sketch this separately. And notice how we can actually break that down even more. So 68% is between one standard deviation below the mean and one standard deviation above the mean. So since the distribution is symmetrical, that means from the mean to one standard deviation below the mean is 34%. And between the mean and one standard deviation above is another 34% for a total of 68. Well, if that's 68% and two standard deviations on either side is 95%, well, 95% less 68% and divide that by 2, that means that this area in here has to be 13.6%. And this area here has to be 13.6%. I'm going to round that off for our purposes to 14. So 38 and 14 and 38 and 14, that would represent pretty close to our 95%. Okay, that would leave below two standard deviations below the mean. That would leave, let's see, two standard deviations below the mean and two standard deviations above the means represents 95% of the population or outcomes. Well, what does that leave? It's going to leave 5%. Again, since it's symmetrical, that means that 2.5% of the population or this distribution is below this, or is further than two standard deviations below, and or two standard deviations above. So it adds up to, it's going to add up to 5%. So it's 2.5 at this tail and 2.5 at this tail. Okay, so let's take a look at that from the perspective of some real numbers. Okay, so I'm going to start out with this distribution I just mentioned. I'm going to say the mean for the population that we're looking at, the mean weight was 150 pounds, and the standard deviation for the weights is 20 pounds. Okay, so right in the middle of this population is going to be our 150 pounds, if presuming that this is a normally distributed population. So what's the probability that if I randomly selected an individual, they would weigh more than 150 pounds? Somebody. What are the chances I would pick somebody from this population that weighs more than, I'm looking up there because there's so much deadening silence there. I want to make sure there's something up there. What's the probability if you have this distribution and the mean is 150 and it's a symmetrical distribution, what's the probability that you randomly go in there, grab somebody, and they were more than 150 pounds? 50%, right? The same thing as the probability of somebody being less than 150 pounds. Great. That's as simple, that's as hard as it needs to be. Okay, now, what's the probability that you would select someone from this population that's between 130 pounds and 170 pounds? Yes, 68%, right? That's our empirical rule. That's what our empirical rule is telling us. So what's the probability that they would be between 130 and 150 pounds? Right? Remember, it's symmetrical. 34%, right? Why? Because this is symmetrical, so this area in here is the same as this area in here. I may not have drawn it perfectly, but take my word for it that that's true. Okay, good. Okay, so what's the probability that we would randomly select an individual from this population and their weight would be more than 170 pounds? Let's think about that for a second. A couple of ways we could figure that out, right? First of all, one way we could figure it out is to say to ourselves, well, the mean represents 50%, right? It's going to be above here, right? And if we've already counted for 34%, how much is left? Bingo, that's it, 16%. Okay, so let's go to 2 standard deviations away from the mean. The 2 standard deviations away from the mean means just 2 times 20, 40 away from the mean. So 150 to 110, and 150 to, we're going to add 40 to that, is 190. Okay, so what's the probability that we would randomly select an individual that weighs between 110 and 190? Bingo, 95%. Good, that's 95%. Okay, what's the probability that we would select someone that weighs less than 110 pounds? Well, between here and here, we've accounted for 95% of the population, correct? Okay, that leaves 5%, right? So where is that 5% that's left? Well, half of it is here and half of it's here. So this area is going to be 2.5%. Right? Good, right? Okay, so that's that's what the standard deviation does for us. It allows us to understand or predict what we're dealing with when we look at different parts of this normal distribution. And there's a really ugly formula that's remember, this is all based on probability, right? Starting with the fact that this is, that we assume it to be normally distributed. Those are binomial. Here it is, I have a copy of this formula here. Here's the formula that represents, oops, no, I got another binomial formula. I got it in here somewhere. Let's see, maybe it's this one. Oh, it's this one. There we go. Okay. Okay, I don't need to open it. Preview, I'll just blow it up. Okay, there. What do we have in that formula? We have f of x, right, or y. Sometimes we call that the y-axis, right, f of x. That's the height. The height of the histogram, in our case, is going to be a smooth. We have a probably, we're looking at a normal distribution where we're representing as a nice smooth curve. So that's going to be the height of that nice smooth curve at any point. X is going to represent the particular point we're looking at, like 50.10034 pounds, a person that weighs that exact amount, right? So what is that height equal to? That height's equal to this formula. And what's in this formula? But without killing ourselves to solve the formula, what factors are in here? Well, we have the value x, right? That's our 150 pounds, let's say, minus the mean. Well, for starters, if it was really 150, that would be 0 right off the bat, right? So we can see where that would go. But whatever that value is, 160 minus the mean, divided by t squared, divided by 2 times the standard deviation, times, and this is all over, 1 over, that's the power that we're taking 1, 2, over the standard deviation, times the square root of pi, times e, which is also natural log, which is also a constant, right? These are all numbers, pi and e are constants, they're just numbers, right? But the only factors we have here really are the value we're looking at, mean, and the standard deviation, which are all in this table right here, right? We're going to have all of those factors. So what does that formula represent? F of x. It represents the height at any given point. Here is lower, here is lower. And why is it lower? Because when you solve that formula, that f of x comes out to be a lower number, lower height, right? So we don't need to use that formula. Why don't we need to use that formula? Because we have tables, calculators, we have the empirical formula to help us with these calculations, so we don't actually have to use that formula to determine all these values. Not only that, but that formula is kind of interesting because it only defines a single point, right? So if I were looking at that single point at the height, Well, a line doesn't have an area, right? So that really doesn't do us any good anyway. We like to deal with areas. And for areas, we need a range from one point to another, right? So a straight line like that would not help us very much. Okay, but put them all together, or put a range from one straight line to this straight line, then that gives us an area. We can turn that into a probability. Okay, so let's put this to work. In the document that we have here, let's give it a try. Assume that the heights of adult Caucasian men have a mean of 68 inches and a standard deviation of 4 inches. Find the probability that a randomly chosen individual from this population has a height, and then we have a bunch of selections. I'm going to sketch this out, not because we really need to sketch this out for this simple a problem, but just because I think it might, as these get a little bit more complicated, it might come in handy. Okay, so I'm going to narrow this down so I can put it up here right alongside this. Okay. Okay, so I'm going to sketch this out. So here's our normal distribution. And remember, one other thing I want to mention is this works exactly the same way for all normal distributions. So I'm going to draw one here, which has a mean of 150 and a standard deviation of 20. Right, it says 150. Let's say this is 20 more, this is 20 more, this is 20. Those are our 3 standard deviations, below and above the mean. This is 130, 110, 90, right, so on, right? So those are 3 standard deviations. Let's say we have another distribution, which is a much more select group of people that, say, within a family, within a family group or something like that, where the mean weight, the average weight, is also 150 pounds, but the standard deviation is only, say, 5 pounds. So what would that look like? That would look like this. See, the mean is going to be 150, but the spread is going to be much narrower, right? Well, what do these have in common? First of all, they're normally distributed, so they're bell-shaped curve, and they're symmetrical about the mean. Okay, so now when I'm looking at the percentage of this group, which is between 140 and 160 pounds, right? What is that? That's 2 standard deviations below the mean and 2 standard deviations above the mean, right? Well, for this group, that 95% of the population would also be between 2 standard deviations below and 2 standard deviations below, except in this group, a standard deviation is 20. So that would be represented by people that are between 110 and 190 pounds, right? Works exactly the same way. Doesn't matter if it's a skinny, tall distribution, wide, flat distribution. If it's a normal distribution, if you use its specific mean and standard deviation, you can apply the empirical rule. Okay? Okay, so what does our distribution look like? Our distribution has a mean of, let me help with that. What was it, 68? Okay, our mean is 68. Okay, there's our mean. And what's our standard deviation? 4? Was it 4? Am I right? Okay, and the question was, what's the probability that we'll randomly choose an individual that's more than 68 inches tall? 50%, right. Okay, between 64 and 72 inches. 64 and 72 was, 68, I'm sorry, 68, yeah. Between 64 and 72 inches, that's 4 inches below the mean, which is 1 standard deviation. Instead of writing the height 64, which is what that is, I'm going to write that -1 for the number of standard deviations. And 72 inches is, yeah, okay, I'm going to put that over here. 72 inches is, instead of writing 72, I'm going to write a +1 standard deviation. What's the probability of selecting somebody within that range? 68%, exactly. And what's the probability of selecting someone between 60 and 76 inches? 95%. Again, because it's -2 standard deviations and +2 standard deviations. Okay. Notice how I'm starting to substitute number of standard deviations for the actual value. The actual value that represents -2 standard deviations below the mean is 60 inches. Person that's 60 inches tall would be represented by 2 standard deviations below the mean. Okay, let's take a look at another one of these. Okay, assume the heights of all adult Caucasian women are mean 63 inches, standard deviation of 3 inches. What percentage of women in this population have a height greater than 63 inches? Again, (63) and standard deviation was equal to 3 inches. And let's see, greater than 63 is 50%. Greater than 66 inches. How many standard deviations above 63 is 60 inches? That's +1 standard deviation, right? But we're not looking for the area between certain standard deviations. We're looking for this area here, right? But we can deduce what that area is, right? Because we know that this represents 50%, right? What does this area represent? Anybody remember? Remember, if we had a 1 standard deviation on both sides, this would be 68 or 34 and 34. So just from the mean to 1 standard deviation above is 34%, leaving 16% of the distribution. So the probability of randomly selecting someone that's more than 66 inches tall is 16%. How about less than 60 inches? Is 60 inches. How many standard deviations below the mean is 60 inches? Right, -1 standard deviation below the mean. So this area similarly is 34%, leaving this area to be 16% again. Right? Everybody okay with that? So what's the probability? I'm going to add one to this. What's the probability of selecting someone that is less than 57 inches tall? 2.5, right, 2.5%. How do we get that? How do we get that 2.5%? Well, 57 inches is 2 standard deviations below the mean. If I imagine the area from 2 standard deviations below the mean to 2 standard deviations above the mean represents 95% of the population, right? Then that leaves 5% of it outside of that range. And this area over here represents only half of what's left, because the mirror image of it is above 2 standard deviations, +2 standard deviations above the mean. So that's 2.5%. What's the probability of selecting someone that's above 57 inches tall? That's more than 57 inches tall. Right? Well, the only area you're excluding is this area right here. And we already know that's 2.5%. So above 2.5%, 97.5%. Okay. Now remember, all of this is approximate, right? Because we're just using this rule as a convenience. We're going to find out that we're lying when we say 95%. We're lying a little bit on that 2 standard deviations. We're lying a tiny bit, but enough to be important to us as we move on. Okay, let's try one more of these. How are we doing online? Any questions online? Okay. Yeah. Okay. No, we seem to be doing okay online. Good. All right. So let's go to the next one here. Adult gestation time. Okay. Gestation time in humans is a mean of 266 days and a standard deviation of 25 days. Okay, I'm gonna draw that now. And again, you don't have to draw this necessarily, but it'll help you avoid mistakes, right? So the mean is 266 days. That's our mean, put it right in the middle. And yes, and our standard deviation is equal to 25 days. Anybody know if that's reasonable? See, the nursing students usually have an opinion about this, but the FE students never have an opinion about this because they don't know anything. The nursing students actually have to know stuff. So nobody knows. Is that right? It's 20. What is two? How many months is 266 days? Is that 9 months? Let's somebody figure that out. Okay. While we're talking about that, somebody figure it out and find out if this is realistic. What's the probability that a baby would be born at greater than 291 days for a mother? If this is true, first of all, number one, we know right away it's not really a normal distribution, right? It's going to be skewed because you're going to get very few babies that are born far away from above the mean, but you're going to get more early birth babies, premature babies, low birth weight babies, early babies, more than you would get nowadays, particularly when they induce labor, if it goes too long or something like that. Probably not really normally distributed. We're going to use this as an example. So what's the probability that you would get a pregnancy that lasts more than 291 days? What's the difference between 291 and 266? How much? Well, let me do this. I'm going to go over here 291 minus 266, and that comes out to. What does that come out to? Somebody help me here. 4 and 4, 24, 25, right? Right. So that's one standard deviation above the mean. I'm old. It takes me a little while to figure that out. 20 years ago, I just looked at that and said 25. Okay, so it's 25, right? What did I just do there? I just took the value I'm interested in, x, and I subtracted the mean, right? So that's what I just defined the difference, the number of standard deviations. I took x, which was 291, the value I was interested in, the number of days, minus the mean, came out to 25. And now I want to see how many standard deviations that represents. Well, it's 25. So 25. Oh, I could have just said, just divide by 25, and it would have told me how many standard deviations it is. It's one standard deviation, right? Okay, so kind of what I did there was just in my head say x minus mu, and then divide the result by the standard deviation to get the number of standard deviations. Okay. I'm learning how to take these formulas and sneak up on you with these formulas. Okay, that's what I'm doing. I'm slowly sneaking up on you with these formulas. Okay, so that represents an easy way for me to calculate the standard deviation, right? So let's see, that's one standard deviation above the mean. So what percentage of these births are going to be above 291 days? Right, that's one standard deviation. What's left here? You remember what's this area in here for one standard deviation? That's going to be 34, right? Okay. So what's left over here? 16% of the birth, right? Okay. How about what percentage are less than 241 days? 241. I make believe that I really can't do this in my head. It might be true. Let's make believe. Let me go use that formula I just made, right? X minus the mean, the value I'm interested in, minus the mean divided by the standard deviation. So x is 241 minus the mean is 266 divided by the standard deviation is 25. So that's equal to 20 minus 20. That's minus 25, right? Because I have it in that order. It's minus divided by 25. So that's equal to minus 1. So in other words, that's one standard deviation below the mean. That's my minus 1 standard deviation, right? So less than 241 days, what is that? That's also 16%, right? Because only one standard deviation. So what's the probability that you would have a birth that's premature or that's late, that's less than 241 days or greater than 291 days? That's union, right? Could be either one. It's going to be 32%, right? The 16% here and 16% here. And what's the probability that you're going to have births that are between 241 and 291? Well, since that's 32%, that's going to leave our 68% in the middle. Okay, which we know is that minus 1 plus 1. Okay, let's take a look at this. Okay, good. Okay, ignore this beginning part here. We'll get to that in a second. Let's try this next one, okay, which is going to throw a little bit of a curve into this whole thing. Okay, I hope it's going to throw a little bit of a curve. That's what I intended. Yeah, it should. Okay, so the heights of adult U.S. women have a mean of 63 inches and a standard deviation of 2 inches. What percentage of women would you expect to have a mean height? Okay, let me sketch this first. Okay, mean height of 63 inches, standard deviation of 2 inches. Standard deviation is equal to 2 inches. What percentage of women would you expect a mean height less than 63 inches? Easy one again, right? 50%. Less than 62 inches. Oh, wait a second here. Here's 62 inches, and we're looking for the area below that. Okay, let's see. I'm going to use my formula to make it simple. X minus mu over sigma, right? In other words, 62 minus 63, that's a -1, right? 62 minus 63, if I keep these in the right order, that's equal to -1 over the standard deviation, which is 2. So that is -1/2, right? Half of a standard deviation below the mean. So I'm calling it -1/2. You know, now's a convenient time since we keep referring to the number of standard deviations below or above the mean. Now's a convenient time to give that value a name. Anybody want to suggest one? Give me an idea. What would be a good name for that? How about that Z, right? Remember we were talking about Z before? That's the Z-score. The Z-score represents, or the Z value represents the number of standard deviations below or above the mean. Okay, so the Z value here is -1/2. One half of the standard deviation below the mean is what represents the value 62 inches. 62 inches, was it? Yes, 62 inches. Right. So another way of saying 62 inches in this distribution is to say -1/2 standard deviation below the mean. Negative already implies below the mean. Okay, so I'll also call it -0.5. Maybe it's even nicer, a little bit easier to call it -0.5, half a standard deviation below the mean. Okay, so now how are we gonna figure that out? We can't use our empirical formula anymore, right? Because our empirical formula, unless we want to visually try and figure it out, right? Empirical formula only works for whole numbers of standard deviation. We have to have another way to do this. Well, remember that formula we just brought up, right? We could solve that formula for what the height is and try and find the difference and do an integral to find the area between 62 and but we don't want to do that because we want to be here like only for less than we don't want to spend a week on this problem, right? So or go back to calculus, right? So instead, we're going to fall back on either a calculating device or a table to help us figure this out. Remember that standard normal distribution that we talked about? That distribution that represented a specific, that normal distribution that was specifically a mean of 0 and a standard deviation of 1? Well, someone has gone to the trouble, many people actually have gone to the trouble, of using that standard normal distribution and doing those complicated calculations to figure out what all of the areas would be, what areas would be represented by any value of the z-score. Okay, so if we go to a normal distribution table, which is in your book, and which I usually put it on the one I usually use is the one from a textbook that we used to have called the Gestation. I like that one particularly. Find this. Where did it go? Here's this K. Oh yeah, guys online are ahead of you guys. Got a Z. I immediately got a Z value from one of them. Let's see. Okay. Standard normal distribution. There we go. Z table. This is the Gestation one. And it actually has 2 pages, right? There's 2 pages for negative values and for positive values of z, either side of the z-score. I think I also have your, yep, this is the one that's in your book. And it looks very similar. Okay, it's got a table like this, and it's got a bunch of decimal places up here, and then it's got values over here, and then numbers over here. I'm going to show you mine for starters. I like mine better because it's a little prettier, right? Purple. I think the CUNY colors are purple, right? Aren't they purple? Am I wrong about that? I like my table better because it uses the CUNY table. It's exactly the same table, by the way. The only difference is that the z-scores are on the left-hand side on this table, and the z-scores on the right-hand side on the other table, if you look at it. But if you look at this table, what this table tells you, that if you want to look up a z-score, like a z-score of the one we were just looking at was minus 0.5, right? All I have to do is go down here and say minus 0.5. That's our z-score. Now, a lot of times we'll want a little bit more precision than that. So we want 3 significant digits for our z-score very frequently. So I need, for instance, 1.4, and I want another digit besides that 1.4 sometimes. How am I going to do that? Well, in this table, the 3rd digit is represented by a different column to the left of that number. So if you were looking up for a z-score that represents negative 1.40, it would be this number here. Negative 1.41 would be this number here. I'm going to go up to 3.2 just so you can see the top of the table. Negative 3.22, the last digit being 2, would be this number here. Negative 3.27 would be this number here, right? What do those numbers represent? Well, if I go to a z-score of 0, 0.00, what is that area? What is that? I gave it away. What does that number 5.5000 represent? It represents an area. It represents 50%. And the z-score represents what value? The z-score is 0 is what? It's the mean, right? So we know that 50%, the area of 50% is associated with the mean. If I look at this little chart up here, what these areas throughout this table represent is the area to the left of the value of the z-score. So if the z-score is 0, you're right in the middle. So the purple area would be the area to the left of the mean, which is 50% when the z-score is 0. Okay, so now what happens when the z-score becomes positive? Okay, that's when we use the other table. When the z-score goes above the mean, then the z-score values are positive, and as you go up, right, that line is moving to the right. The z-value is moving across this way. 1 standard deviation, 2 standard deviations, 3 standard deviations, 3.0, so on and so forth, right? But the table is still giving you the area to the left of that value. So that's important to us. Because you got to remember how this table is being used. So if I want to know, the question was, what is the percentage of women you would expect to have a height less than 63 inches, right? 50%, less than 62 inches. That was a z-score of negative 0.5, right? Well, okay, we're going to use the first table, negative 0.5, and it's negative 0.5 even, so it's 0.50, right? 0.50, 0.050 is this first number here, 0.3085. What is that number again? That's the area of the distribution to the left of that value, below that value. So in other words, the area that we're interested in would be about 31%, right? What was it? It was 0.3085 or something like that. Actually, like 30.85%, almost 31%. So what would be the probability of randomly selecting a woman from this population that's taller than 62 inches? Going to be 1, bingo, 1 minus 0.3085. Okay, good. All right, so we're making good progress here. Let's try the next one. What's greater than 66 inches? Greater than 66 inches? What's our z-score going to be equal to? And I'm going to get into the habit of actually calculating this out so I keep the signs correct. If nothing else, it's going to be 63 Did I do this right? 66 minus, right? X is 66 minus 63, the mean, over the standard deviation, which is 2. And that's 3 over 2, or it's going to equal 1.5. And it's asking for the probability of being larger than a z-score of 1.5. Let's go back to our table. Our z-score is positive this time. 1.50 is 0.9332. I'll call 93.3, I'll call it. Remember, what area is that? That's the area to the left, right? So 66 is going to be out here. And this area from here down is 90, what did I say it was? 93.3 or 0.933 something? 0.9, I'm going to call it 0.9, yeah, 0.9332 or something. Something like that, right? The area to the left of that is that, but is that what the question asked? What's the probability of being above that? So it's going to be 1 minus 0.9332. Okay, how are you guys doing online with this? Okay. Anyone faint? Anyone hang up? Okay, good. All right, excellent. Okay, so let's move on to another one of these. Percentage of elementary school teachers, and yeah, there's a lot of elementary school teachers are pickety in the States, right? Teachers in the United States has a mean of $32,000 and a standard deviation of $3,000. Find the percentage of teachers you would expect to have a salary greater than $36,000. Okay, so let's give that a try. So I'm going to open up a new one. Okay. Okay, so let's see. Here's my normal distribution. Again, you're always dealing in the same. I'm always drawing it the same way. I'm not drawing it tall and skinny, fat and wide. I could, some of them might be more appropriate to draw this way, right? But I'm drawing all the same way because it's irrelevant to what the real shape is, right? Because the calculations I'm going to do are based on the mean and the standard deviation, not the actual numbers that I'm dealing with, right? I'm converting them into z-scores. Okay, so percentage of the mean of 32,000 and standard deviation of 32,000 and standard deviation of 3,000 greater than 36,500. Put that over there, 36,500. So how am I going to do this? I'm going to calculate a z-score is equal to x minus mu over sigma, and that's going to be equal to 36,500 minus 32 over 3,000. And what does that come out to? 32,000, 4,500. Is that right? I think so. 4,500 over 3,000. That's also 1.5. Okay. I'm going to lie. Let's cheat. I'm going to call, because I want to use the table a little bit differently. I'm going to call the z-score 1.63. A plus 1.63. I'm just picking that arbitrarily because I don't want it to be a nice even number. Let's go to our table. Let's go to the video. Anybody remember, what was his name? Werner something or other. Werner. He used to be a newscaster, a sportscaster on Channel 5 in New York City. You guys are too young for him. No, not all of you guys are too young to remember this. His catch line would be, let's go to the videotape. And they would, never mind. All right. Nobody remembers him. Okay, so at any rate. So we have a z-score of plus 1.6, what did I call it? 3. Okay, so what value, what area are we looking at? 1.63, 1.6012. So that represents an area of 0.9484. 0.9484. So almost 95% of this population, or the probability of picking an individual from this population, would be below that point because this table always works to the left. Do all of these tables always work to the left? The answer to that is no. You may well come across a table that works this way, where it gives you the z-score. Right? Z-score. If you put in the z-score, it gives you the area between the mean and the z-score. Many of the tables do that instead of always going to the left, right? But if you stick with the same table, you don't have to worry about that. Okay, so, all right, just remember to check if you use a new table. Less than 28,000. I'll tell you what, you do less than 28,000. What's your probability of selecting an individual from this population that makes a salary of less than $28,000? Remember, Z is equal to X minus mu over sigma. Oh, 30, what is that, 30? Less than 28,000. What's that? 28,000 minus 32,000. So, let me try that again. 32,000. Needs another zero. Is that right? The mean is 32,000. I keep forgetting. And I can't get across that far. 32,000 is the mean, and we're asking about 28,000. That should be 28,000, by the way. Not $28. Okay, so 28,000 minus 36,000 over, what's the standard deviation? What's 3,000? Okay, you guys tell me, anybody got the percentage? What was that? Percent? That's a z-score? Hang on a second. It's asking for what's the probability, find a percentage you expect to have a salary below 28,000, right? Okay, so let's figure this out. Okay, so 28,000 minus 30,000 is negative 4,000, right? Divided by 3,000 is going to be negative 1.3, right? So you got the z-score right? So now we got to look up that negative 1.3. Negative 1.3 is going to be the first chart, right? The negative chart. So we know immediately that it's going to be less than 50%, right? Below that level. So 1.3 is 90.9032. So the area, excuse me, I made a mistake there. I'm on the positive side. Negative 1.3 is 0.0968. Okay, negative 1.3 is 0.0968, I think it was, right? So I don't have to make any conversions because I was already looking for the area below, not above. Yes. You're right. Yeah, let's go back. Okay, 1.33, I should really use 0.0918 instead. 1.8 instead of 6.8. Right. Z-score is a little bit bigger, a little bit further to the left, right on the negative side. So the area to the left of it is going to be smaller. Okay, let's look at something interesting now. Remember before I told you that the empirical rule says, what does the empirical rule tell us again? For two standard deviations. What does it tell us about two standard deviations? Yeah, 95%. Yeah, let me see. Let's see. So let's see. Okay, 95%, 95%. So with negative two standard deviations, this area should be 0.025, right? 2.5%. Let's see what the table says it is. Okay, negative 2.00, .228. It's not 2.5%, 2.25%. Well, that's interesting. The empirical rule is only an approximation. This table is giving us a more accurate value for what really is two standard deviations below the mean. Well, what z-score actually represents 2.5% of the population being below the mean? Okay, well, how can I figure that out? Well, how about if I look up the area in here and then see what z-score is represented by 2.5%? So let's find these 2.5% in here. 2.1, that's going down, let's go up. That's too far up, 2.5, 2.50. So what z-score actually rarely represents that 95, that 95% below and above the total, the middle of the population. The z-score that represents that is not 2, but it's negative 1.96. Negative 1.96. So what do you think is going to happen when I look at the other end? And I want to know what z-score represents the value that represents the middle 95%, but on the upper end. So it leaves only 2.5% on the tail outside of that area. What do you think that's going to be for 95%? If this is negative 1.196, it's going to be positive 1. Let's take a look. Yeah, let's take a look at positive 1.96. Positive 1.90, 1, 2, 3, 4, 5, 6. Sure enough, 97.5% of the distribution is below that number, leaves 2.5% exactly above that. And what number is that? That's also negative 1.9, except it's a positive 1.96. So this table is more accurate than the distribution is. Okay, so let's take a look at another way to do this. Okay, so, actually, before we move on to that, I want to do this problem again. Actually, I want to do the one before it. Did I do the one before? I didn't do. Did I? I didn't do the one before it. Body temperature. I'm going to do this one, body temperature one, using Excel instead of the table. Okay, so I'm going to draw it anyway. Okay, so I'm going to draw it anyway. Let's see. By average body temperature of adults, 98.6, standard deviation of 0.6 degrees Fahrenheit. Okay, I'm not going to bother asking the epi majors and biostat majors if that's really true, because they won't know anyway. So 88.6, and sigma is equal to, let's see, 0.6, 0.6 degrees Fahrenheit. Okay, good. So now, what's the probability that a randomly selected individual has a mean body temperature greater than 99 degrees? Okay, so what's the z-score for 99 degrees? Z is equal to x 99 minus 98.6 over 0.6. And what does that come? That's a positive number. It's positive 0.4 divided by 0.6. And I know you're going to annoy me about this again, so I'm going to say it's 0.667, right, Hondo? Okay, good. Okay, so let me get away with that, okay? All right, so 0.667. Oh, okay. So actually, I'm not really going to be able to use that extra digit. I'll go to 0.067 probably when I go to the table. But actually, in Excel, I might be able to use that. If I use the table, that was a positive number, 0.06. I could only go to another digit, 0.067. So I'd be using that number there, 0.71. 71.5% of the distribution is below that number. The remainder is above that number. Okay, but now let's take a look at Excel. Did I do something wrong? What's that? Oh, I was in the wrong line. Okay. All right. Yeah, I'm rushing. I don't want to run out of time. I still want to get the binomial distribution, so I'm rushing a little bit. Okay, let's go to Excel. Okay, I'm going to blow this up. Okay, so I'm interested in knowing what value that z-score is going to give us. So I'm going to see if there's some functions here in Excel. Actually, I'm going to open up something I have here as well. I need to get to the. Okay, here we go. On Blackboard, I gave you I gave you a summary on Excel of the different statistical functions that might be useful for this. Okay, so the function norm S dist, standard normal distribution. If you put in equals norm S dist, it's going to ask you for what the z-score is. If you put the z-score in, it'll give you the area to the left of the z-score. So if you know the z-score, you can just put it in there and find the area to the left of that value. The value norm dist, well, if you put in x, mu, sigma, and the value true, I'll talk about that in a second, that'll give you to the area to the left of that z-score. Right, so that, if you know those, that'll save you the trouble of calculating the z-score on your own. Right, so, and then if you want to go the other direction, if you know what the area is and you want to know what the z-score is, you can put in the area, below that value, the mean, the standard deviation. It'll give you the value of that number, that age, that weight, that height, that gives you that norm. And norm S inverse, if you put it in the p-value, it'll give you that the z-score for that p-value, that probability, that area of the distribution. In other words, the area 0.025 will give you back a z-score of negative 1.96. So let's use these. Norm S dist equals norm S dist, parentheses, and it asks me, what's the z-score? You ask for the z-score. What's the z-score? We just calculated 0. I thought it was 66 something. Which one was it? What was that? I'm sorry. Yeah. Point. You beat me to it. 0.667. I'm going to put in. Okay. I'm actually going to use that extra digit. I'm going to hit enter, and it gives me the area of 74.76. That's the area below that z-score. It's a positive z-score. That's the area below that z-score. If I want to know the area above that z-score, I just say equals 1 minus this value, and that would give me the area above. Add them together, then come up to 100%. Right? So, how about if I do it the other way? Use norm dist instead of norm S dist. This time it's asking for x, the mean, the standard deviation, and cumulative. Okay, so x was what again? Anybody remember? 98.6? No, 98.99, right? The mean was 98.6. Yep. The standard deviation was 0.6. And now I got to put cumulative, or I got to answer cumulative. That's going to be a true or false. If I answer false, it's going to calculate that line, the height of that line. It's not really an area of that line. It doesn't do us any good to calculate that. We want an area, right? So false means it's just going to give me that exact value, not an area. So if I type in true, it's going to give me cumulatively, it's going to give me the whole area up to that point. In other words, from that point down, right? So that's why I always put in Q there, because I don't even know why they give me the option of false. And hit enter, and I get the same value, but pretty much the same value that I got before. The only reason the value is different is because I only went 3 digits before, 0.667. If I went, what, 0.66666, up to how many ever digits that this would tolerate, then I probably would have gotten exactly the same answer. Okay? You guys are okay with this? Yes. There you go. It's norm S dist, and I put in the z-score. Okay, I can't blow this up, unfortunately. Let me see if I can. No, it's not going to work. Okay, and the next one down here was norm dist, and for that one I put in x, mu, the standard deviation, and true for cumulative. Right. So one of them forces you to calculate the z-score before you can use it. The other one you bypass calculating the z-score. Right? And let's say I have this area now, and I want to know, well, what z-score is represented by the value 74.74, so on and so forth. Well, I can use norm inverse, parentheses, I got norm S inverse, parentheses, and if I put in the probability there, this 74%, the area, it'll give me back the z-score. So you have on Blackboard, you have this Excel table, right? And you can play around with that later on. And actually, so if this is what you have and this is what you want, you use this function. If you use this function, this is what you have, this is what you'll get. This function, this is what you input, this is what you get. This function, this is what you input. The P means the probability or the area of the distribution to the left of that value. And that's what you'll get. Okay, so these are the inputs, these are the results that you get in Excel. Okay, so let's move on from there. Because the idea of this binomial distribution. Okay, there's some more stuff there, but you can play around with that. Pretty much the same thing. This is pretty much the same stuff we just discussed in using the Excel. Okay, another document here that discusses the binomial distribution. Okay, so let's see what the binomial distribution is all about. Remember we had our, our probability table where we were looking at situations where we could only have two outcomes and the outcomes were mutually exclusive. For instance, we were looking at the probability that people might have diabetes. Well, each individual that we would pick from a population that either have diabetes or they don't have diabetes, right? It's dichotomous. I mean, two values, and they can't have both, right? They have to have one or the other, and you can't have both, right? So that's mutually exclusive. Similarly, left-handedness, left-handed or not left-handed. I hate to say that was a bad one because some people, yeah, forget that one. Okay, so male or female, again, now we have a problem with that nowadays. So it's kind of hard to find something that's perfectly dichotomous. But let's say diabetic and not diabetic at the time. So let's say that we have a population, right, where we're going to sample people from that population. And let's say I'm going to sample 100 people from that population. If 10% of the population, if we know 10% of the population is diabetic, right, what would we expect to happen when we sample 100 people? How many people with diabetes do we expect to get? We expect to get 10, right? 10% of the population diabetic, 100 people, we expect to get 10. Are we always going to get 10? No, because by chance we might get fewer or more on any given time. However, if I did this over and over again, right, most frequently I would get 10. So I'm going to build a histogram. I'm going to do it over and over and over and over again. My most frequent outcome would be 10. My next most frequent outcome would be either 9 or 8, 9 or 11. My next most frequent outcome would be 7 or 12, and so on and so forth. What is this starting to look like? It's starting to look like a normal distribution, kind of, but a special case of a normal distribution. This is a binomial distribution, right? But not quite exactly the same shape, but has a lot of the same properties. We can, for a large sample size, big N, right, assuming that the number of people that are diabetic is at least 15 people that we would expect to be diabetic is our mean, and that people that would not be expected to be diabetic is also at least 15. Like this wouldn't qualify. We would need, let's say we would do this with a population of 1,000. Instead, we'd expect 100. So if I looked at this distribution I would get from doing this over and over again, sampling 1,000 people, 1,000, and so on and so forth, what would I expect to be the average number of people that I would find in the samples? I'd expect it for 1,000, 10%, I would expect it to be 100, right? That's going to be my mean outcome for that repeated sample. How do I get that? One way I can get that is just saying N times the probability of being diabetic, right? N times P, right? That's 1,000 times the probability, which is 0.1, is equal to 100. Well, now, it looks kind of like a normal distribution, but in order to do calculations conveniently with this, I would need to know how are things going to be distributed here. In order to be able to estimate from this distribution that I'm imagining that's kind of normal, I would really need to know what the spread is like. And in the normal distribution, I would be using the standard deviation. The way we're going to calculate or estimate standard deviation for this binomial distribution is we're going to say that it's going to be equal to the square root of the sample size times the probability. From now on, we're going to call that the probability of success. The probability that the person you sample is diabetic, right? Probability of success times 1 minus the probability of success, probability that they're not diabetic. So for this group, it's going to be the square root of 1,000 times 0.1 times 0.9. Okay, let's figure that out. 1,000 times 0.1 times 0.9. Okay, find the square root of that. It's going to be equal to about 9.5. So our standard deviation is equal to 9.5. Right, so if I asked you, what's the probability that if we took a sample of 1,000 people, that in that 1,000 people, we would find fewer than, let's see, 100, it means 90 and a half people that are diabetic out of 1,000. What's our z-score? Our z-score is equal to 90.5 minus 100 over our standard deviation, which is 9.5. Right? 90.5 less from 100 is going to be equal to minus 9.5 over 9.5 is -1. Right? Z-score is -1. So what percentage of people would we expect? How often would we expect to get a value where there's fewer than 90 and a half people that are diabetic out of our 1,000 people? We would expect that to occur less than, looks to me like one standard deviation, so roughly about 16% of the time. Right? That'll only occur about 16% of the time. So to be more accurate, I could go to my normal distribution. Okay, so that's one way we can look at this distribution. Let's take a look at another way we can look at it. Okay, let's take a look at this. And there's a function in Excel that's going to help us out with this. A study indicates that 10% of nursing home patients are diabetic. How convenient. But we're going to work with small numbers now. Small numbers, we don't want to use the normal approximation to binomial distribution because it's not dependable with small numbers, right? So small sample sizes. So since we're only interested in a small sample size, 10 patients, right? We actually have to calculate all of the possible outcomes, or probability of being diabetic, the first patient not diabetic, and then a tree not diabetic, not diabetic, and it's going to be impossible for us to figure out that easily. We could apply this formula, which is a little bit more convenient. If we can't find it again, I closed the folder. And I'm ignoring you guys online for too long. I'm going to be looking over there in a second. Okay, where to go? Nope, not that formula. This formula, right here, right? Okay, where the n is the sample size, x is the value we're interested in, like 9 out of 10, 4 out of 1 out of 10, 2 out of 10 probability. P is the probability of success. Q is the probability that they're not success, failure, that they're not diabetic. So all of these, we can put all this together. That's all we have there, and find the probability that we would get that outcome. We could actually do this if we wanted to, right? We're using some tools like Excel. We could simplify that a little bit and actually do it. But we have a tool in Excel that will actually calculate it for us or estimate it for us. I'm going to open up Excel. And I'm going to go in here, and I'm going to use a function called binom.dist. There's a few versions of this. There's binom.dist, which may or may not be more accurate, but let's keep it simple. Let's just use binomial disk. When I hit the parentheses, whoops, got to put an equal sign in there. When I hit the parentheses, it comes up and prompts me. It wants number S, number of successes. Right? We know what that means now. Trials, number of trials is the sample size. Probability of success, that's the probability any particular individual is diabetic. And cumulative, we're going to look at what that means in a second. So let's see, we're talking about what's the probability that exactly one patient will be diabetic out of the 10 randomly selected ones. Okay, so let me go back to Excel. One patient out of 10. Put Excel up. There it is. So I'm gonna do this up here. A little bit more convenient. Equals binomial disk parentheses number of successes. That's exactly 1 out of 10, right? Comma number of trials is 10. I'm going to sample 10 patients. Comma the probability that any individual patient is diabetic is 0.1. Comma and cumulative. Cumulative is asking me to tell it whether I'm interested in just exactly that outcome, just for 1 out of 10, or if I want to include other outcomes like 0, anything below 1. That's kind of like our z-score. The z-score is here. The table gives you the probability below that, right? It's asking me, do you want that? Remember when I said the z-score? When I was looking at the z-score, I said, don't bother ever putting false in there. Because if you put false in there, you'll just get that line, right? It has no area. So in this case, it's the same deal. It'll give, say true, it'll give you cumulative, everything below that. In other words, if you put in the number, instead of 1, you put in 4. It'll give you the probability of 4, 3, 2, 1, and 0 patients out of 10 being diabetic. So true will give you a cumulative. If I'm only interested in exactly 1, I put in false. And the reason why I can use false here is because with the binomial distribution, that's a discrete value. That's an actual frequency that'll occur. Remember, it's got a bar and the height, unlike when you do it with the normal distribution. I'm going to hit enter, and the probability of getting exactly 1 person, that's the most likely outcome, isn't it? Is 0.03874, 39% roughly. It's still more likely that you'll get a different number than 1, even though that's the most likely outcome. So that's for exactly 1 person, right? So I'm gonna center that. Oops. There's for exactly 1. Okay, what's the probability for 0, right? So that's going to be equal to binomial disk parentheses, and I'm going to put 0 outcome. Okay, trials is 10, comma probability is 0.1, and I could put in true or false here. I get the same value because there's nothing below 0 anyway, right? So I'll just put in true for the hell of it. Okay, but that's a little less likely, right? But it's the closest other value to this. Well, how about for 2? Right? How about for 2? How about for 3 out of 10, 4 out of 10, 5 out of 10, 6 out of 10, 7 out of 10, 8 out of 10, 9 out of 10? How about what's probably all 10 of them? Well, I'm going to say equals binomial disk parentheses, and I'm going to say, okay, for 2, instead of putting in the number 2, I'm going to click in here to its value 2. Comma, trials is 10, comma, probability is going to be 0.1, comma, and I'm going to put false because I only want the value for that particular outcome, 2 out of 10 patients being diabetic. And you know what I'm going to do now? I'm going to copy this down so it repeats it for 3, 4, 5, 6. And look at that. The probability of 10 out of 10 being diabetic is ridiculously small. And we know what that is, right? That's 0.1 times 0.1. That's 0.1 to the 10th power, right? Because all of them would have to be so on and so forth, right? So at any rate, so what do you think I'm going to get when I add all these up? Right? What's the other property of this idea of mutually exclusive and independent? They're all going to add, or you can add up all the probabilities. So the probability of getting exactly 0 is that, 1 is that, is 2 is that, and so on and so forth. It gets less and less likely as you get further away from the most common outcome, which is 1. I'm going to find the sum of all of them, and sure enough, it comes out to be 1. Okay. Let's take a look at an interesting way to use this function. Remember I said true and false for the cumulative or not? What if I asked you what's the probability of having 2 or less diabetics out of 10 in a sample of 10? When you sample 10 people, right? Well, one way you could do that is you could take the sum of the probability for each 0, 1, and 2, 2 or less, and then you could figure it that way. It's 92%. Well, another way we could do this is to say equals binomial disk, parentheses, and instead of saying that, I could say, let's see, I want 2, comma, 10, comma, 0.1, comma, except now for cumulative, instead of saying true, instead of saying false, I'm going to say true. And that's going to give me the combined probability for 2, 1, and 0 as an outcome. And it comes out the same way as if I had done the individual ones and added them together. So what's the probability that I would get fewer than 4? Let's do that. Equals binomial disk, parentheses. Let me move this over. Parentheses. So fewer than 4. What should I put in here? 3. Exactly. I need to put in 3 because I want fewer than 4 means 3, 2, 1, and 0. You got to be a little careful with parsing the English, the language in here. Binomial disk 3, comma, where am I? 10, comma, 0.1, comma, true. And that's the probability of fewer than 4. What's the probability of 4 or more? 4 or more. That would mean everything, start with 100% and subtract 3 and less. Didn't we just calculate 3 and less right there? So it's going to be equal to 1 minus the value for 3 and fewer. And that's the probability for 4 or more. Okay? You have some other problems that you can, on that page that you can play around with. And I think we're about to call it a night, except I want to make sure there's any questions.